Good morning, gang. That's not going to finish in time, is it? Okay, that's okay. So, today we need to continue our discussion of trig sub. It's a pretty full day, so I'll ask you forgive or understand if we just jump right in. Last time when we talked about trig sub, I did my best to present it gently, you know, motivation, right? Here's why we want to do this, and kind of here's how it works. Today it's going to be a little bit more dry. Today's the 10th. First, a quick note about the homework. Homework 5. Instead of having it be due next Monday, it's due next Friday. Which is the day of the test. It didn't seem fair for me to dump a heavy homework set on you and then have it be due on the Monday in a week where you have the test on Friday. It seemed more fair to just let you work the homework right up to the day of the test. So after the test, we're going to go back to our normal open and close on Monday thing. But since the test is next Friday, it just seemed like the right thing to do. So you've got a little bit more time on homework 5. That doesn't mean you shouldn't be getting started on it right away. You should. You absolutely should, because it's a long homework set. And more importantly, because there will be the study guide coming out this Friday, which is also due next Friday on the day of the test. So in order to avoid too much overlap, you need to be working very hard to make sure you're caught up now. I would say that by this Friday, you want to be completely done with homework 4. Got to be done with homework 4, and about halfway through homework 5. That's where you want to be. So finish homework 4 ASAP. Definitely before Friday, before this Friday. And try to have half of homework 5 done by this Friday. The study guide is not going to be terribly long. It will just be like 1 or 2 problems from each section. But you don't want to have to do a whole bunch of homework and the study guide leading up to the exam. So definitely make sure, yes, it should be, Rakib. Definitely make sure to have homework 4 done as soon as you possibly can. Ideally, it's already done. Of course, it was due Monday, but it was a long homework and we missed last Friday, so I understand if it's not, but get it done. Try to get it done today, definitely done before Friday. And then homework 5, you want to have a good chunk of it done by this Friday. That way you're not too overwhelmed next week as you prepare for the test. So today, we're doing more trig sub. I want to begin by reminding you that trig sub Bible from last time, the kind of chart that tells you what to substitute when. It looks like this. The left-hand side is your integrand contains, and then you're going to substitute this thing because of this thing. So I'm going to add an extra column to our trig sub Bible. If your integrand contains something like the square root of some constant squared minus your variable stuff squared, and maybe it's under a square root. It doesn't have to be under a square root, but usually it will be. Then you're going to want to substitute u equals a times the sine of theta. And you want to do that because a squared minus a squared sine squared theta is the same as a squared cos squared theta. So while the square root of this is nasty, the square root of this is nice. It's the Pythagorean identity. Oh, I see. So Rakib and Shen are both saying that they cannot get the video from Monday's lecture to work in YouTube. That might have something to do with that link. There was a little bit of weirdness when I tried to when I went to upload the video, it like stuttered and had to restart. So I'll take a look at that and make sure it's working. I'm sorry if there's a problem there. I will take a look. But for now, we're going to continue with this. If your integrand contains something looking like the square root of some constant a squared plus some variable stuff u squared, then you want to substitute u equals a tan theta. And you're going to do that because a squared plus a squared tan squared theta, that's the same as a squared secant squared theta. That comes again from the Pythagorean identity, 1 plus tan squared equals secant squared. And then the last bit of your trig sub Bible says that if your integrand, this is an a here, if your integrand contains something like the square root of some variable stuff minus some constant squared, then you're going to want to substitute u equals a times the secant of theta, because a squared secant squared theta minus a squared, if you factor the a, you get secant squared minus 1. That's the same as a times tan squared theta. So each of these substitutions comes from a Pythagorean identity, which will make the square root clean up nice. Right? Take square roots everywhere here, you see that the ugly square root becomes something nice. Take square roots here, you see that the ugly square root becomes something nice. And if you take square roots here, you see that the ugly square root, oh, sorry, this should be a squared tan squared theta, again becomes something nice. Okay? So this is the idea. This is what trig sub is and why we do it. Each of these, of course, has an associated differential term. Here, du would be a cos theta d theta. Here, du would be a times the derivative tangent is secant squared theta d theta. And here, du would be a secant theta tangent theta d theta. So this really is everything you need to know about trig sub. The places people get stuck here are making algebra mistakes or misremembering their trig identities or not knowing the definitions of the inverse trig functions, which can get you into trouble when you change your bounds. I want to do a few examples today. Last time we did a definite integral to find the area of a circle. Today I want to run through a few more integrals. At least one of them needs to be definite and some of them should be indefinite to get some practice with those because they go just a little bit different. So let's grab a few fun examples. Yeah, what the hell? We'll do this one. I want to make sure I've given enough time for everybody to get this clear in their notes. Take a sip of my coffee. I have to be careful which mugs I use. For those who are done copying, this is a silly joke. So you've got some negative shit underneath a radical, but then it's squared. That says the shit just got real. Real bad math joke. Okay. So the first example we're going to tackle for today is an indefinite integral of the square root of 9 minus x squared all over x squared itself dx. Did anybody need more time on this table, getting this copied down? There was something there in the chat, but I don't have the ASCII character for it. We all good on this? All right, I am going to go ahead then and start on this integral. So, how do we do this? Well, we look back at our little trig subtable, and we ask, does this have anything that looks like one of those? And it does. This square root, right, looks just like one of those. 9 is 3 squared, so according to my trig subtable, I should substitute x equals 3 sine theta, right? The square root of 9 minus x squared looks like the square root of a squared minus u squared, where a is 3 and u is x. The idea here is that u could actually be any linear function of x. That's why I'm using a u rather than an x here. It doesn't always just have to be the variable. So according to my trig sub Bible, this is the sub I should make. I need to calculate my differential, and normally I would change my limit, but since this is an indefinite integral, we're going to do something else. So I'll show you what that something else is. First, dx is 3 cos theta d theta. Now, if this were a definite integral, over here is where I would usually put the stuff that I need to change my bounds. Since it's an indefinite integral, instead what I'm going to put over here is what's necessary in order to go back to the original variable after I implement the substitution. So since x is 3 sine theta is x over 3. And what's going to go in here is a triangle that tells me how theta relates to x. And the trick is SOHCAHTOA. I'm going to think of sine theta as the opposite over the hypotenuse of a little right triangle. So I'm going to come in here and draw a little right triangle where one of the internal angles is theta. I'm going to label the opposite side as x and the hypotenuse as 3. And then I'm going to use the Pythagorean rule to complete the triangle down here. So this squared plus this squared equals this squared. That means this guy has to be the square root of this squared minus this squared. The missing leg of your triangle is usually going to be the square root thing that your integrand contains. So instead of putting work to change bounds in this piece of my trig sub box, here I draw this little triangle instead, and it comes from SOHCAHTOA. All right, let's dive in. My integral, 9 minus x squared, that's 9 minus x is 3 sine theta, so that's 9 minus 3 sine theta squared. That goes under that square root. Downstairs I had an x squared, that's 3 sine theta all squared. And my differential term dx is 3 cos theta d theta. You must not forget the differential term. If you don't do this 3 cos theta piece here, nothing will work out right. Never, ever, ever forget to change the differential. This is part of why it's so important to get in the habit of always writing the dx, because it will remind you, oh shit, I need this piece here. So never skip writing the differential. It will help you remember to not fuck up in the substitution. 3 sine theta all squared is 9 sine squared theta. So both of those instances I can replace by 9 sine squared theta, and my integral will become square root of 9 minus 9 sine squared theta upstairs. Downstairs, outside the square root, I have another 9 sine squared theta. And over here, I still have my 3 cos theta d theta. I could pop the 3 outside upstairs and the 9 outside downstairs, but before I do that, I want to deal with what's going on in the square root. The square root is the thing that makes this hard. The square root is the reason for this substitution, so let's handle that first. So I factor the 9 inside the square root, and what's left is 1 minus sine squared theta. Everything else just coming along for the ride. Of course, I can't cancel the sine squareds or anything like that. This guy is under the square root upstairs, and also he isn't a common factor of the top. I've got that subtraction, so nothing like that is going to happen. But 1 minus sine squared is cos squared. So that square root upstairs is really the square root of 9 cos squared theta. And compare that with what we had in our trig sub Bible. We said the reason we make this substitution here is because we'll end up with the square root of a squared cos squared theta. Well, here's the square root of a squared cos squared theta, just like we said. Downstairs, I still have my 9 sine squared theta, and over here I still have 3 cos theta d theta. Everybody with me so far? The big thing is the Pythagorean thing. The big thing is this to this. Because whereas before I couldn't take the square root because of the subtraction in here, now there's no more subtraction in there. Now it's just multiplication. And square roots play nice with multiplication. I can take the square root of each of those pieces on their own. The square root of 9 is 3. The square root of cos squared is cos. So that's 3 cos theta over 9 sine squared theta times 3 cos theta d theta. And now I'll deal with the constants. Upstairs I've got 3 times 3. Downstairs I have 9. They cancel perfectly. It's all gone. So I just get the integral of cos squared over sine squared. Beautiful, right? So you go from a really challenging looking algebraic integral, square root of 9 minus x squared over x squared, to this rather nice looking trig integral. How do I do this trig integral? Let's see how our 7.2 skills came along. So a question in the chat was about the constants. Did a 1/3 come out? No, I've got 3 over 9 here, but then I've got a 3 over here. So I've got 3 over 9 times 3. That's just 1. So all the constants canceled perfectly. Yeah, so the 3 from the dx, together with the 3 from the square root of 9, make 9 upstairs. And then I've got a 9 downstairs. So 9 over 9 is 1. So all the constants cancel perfectly. Yeah, we see it? It's a little tricky. That's why I waited to deal with the constants until after everything was sorted. Wise to do that. It's okay. That's why we have this moment, right? So if you didn't write down the differential term, you missed that, go back and fix it. Fix it now and get in that habit. And the reason I complain and harp about that is precisely because it's easy to forget. Yeah, there it is. So the trick to integrating cos squared over sine squared is to read it as cotangent squared. And then the trick to integrating cotangent squared is the same as the trick to integrating tangent squared. Who remembers that? Very good. Yep, Simon and Fernando both have it. We apply the appropriate Pythagorean identity. Cotangent squared. If you need to check, right, remember sine squared plus cos squared is 1. Divide everywhere through here by sine squared, and you get 1 plus cotangent squared equals cosecant squared, which means cotangent squared is cosecant squared theta minus 1. So that's what I will use here, because the antiderivative of cosecant is easy. So my integral is equal to the integral of cosecant squared minus 1 d theta, just like that. Don't skip the parentheses either. The parentheses are important. All right, who differentiates to cosecant squared? What is an antiderivative for cosecant squared? Think back to Calc 1, right. So the derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. So an antiderivative for cosecant squared is negative cotangent. So this piece has negative cotangent theta as an antiderivative, and this minus 1 will just give me a minus theta plus c. But I'm not done, because I was asked a question about x's, and I have here an answer about thetas. So I need something to allow me to go from the thetas back to the x's, because it's an indefinite integral. I didn't have bounds, so I didn't change bounds. I'm not evaluating between bounds, nothing like that. Instead, I need to go back to my original variable. And this triangle is the thing that lets me do it. So that's why I put that triangle in there where we would normally put our bounds work. If you look at that triangle, you can read off the cotangent of theta. Here's theta, it's a right triangle, I know all the side lengths. Tangent is opposite over adjacent. Cotangent is adjacent over opposite. So by our triangle, the cotangent of theta, which is the adjacent over the opposite, should be, get these both on the page here, yeah. So by our triangle, the cotangent of theta is the adjacent over the opposite is square root of 9 minus x squared over x. Also, what about theta? Is there a nice way to write theta itself? This is maybe a little bit weirder. It's not x over 3. It's the inverse sine of x over 3. Right? Sine theta is x over 3. So you could solve for theta here by taking the inverse sine on both sides. And you see that theta is the inverse sine of x over 3. So the trig piece, the cotangent piece, we get from our triangle. And the theta piece on its own, we just solve our original substitution for theta. So altogether, my integral the integral of the square root of 9 minus x squared over x squared dx is negative cotangent theta, that's negative square root 9 minus x squared over x, minus theta, that's minus sine inverse of x over 3 plus c. So that triangle takes the place of your bounds work. It's what's going to allow you to go back from your trig stuff to your algebra stuff. If your output involves just a theta, then that's always going to be an inverse trig thing that you get by solving your substitution for theta. I'm going to zoom out so you guys can kind of see it all together. And then I'd like to take any questions on any particular steps. So my final answer is right down here. That's as simplified as that can get. We can't cancel anything here because the square root has this subtraction in it. There's no getting the square root to play nice with subtraction. That's what we talked about at the middle of class last time. Somebody was asking, how did I get theta equals inverse sine of x over 3? Remember, sine theta, the substitution we made was sine theta equals x over 3. And if you take inverse sine on both sides, then you get theta equals inverse sine of x over 3. Rakib asks, is the missing leg of the triangle always the square root part? Not always, but usually. So there are some problems where things are not quite so simple, and you'll need to be a little bit careful completing that triangle. Completing this triangle is never hard. It's always just the Pythagorean rule, right? A squared plus b squared equals c squared. And if you need to go off to the side to do a little side work and find that, that's okay. But it will usually be the square root piece from your integral. Okay. Is that satisfying answers to those questions? Anybody have any other questions or want to go a little deeper on any of those? Yeah, cotangent is adjacent over the opposite. Yep, yep. All right. No, yeah, definitely not wasting any time solving for it. Okay. So the diagram at the top here, my trig sub Bible tells me to make this substitution. And if I rewrite that substitution, x equals 3 sine theta as sine theta equals x over 3, in other words, divide both sides by 3, you get x over 3 equals sine theta. And then I just interpret that x over 3 as the opposite over the hypotenuse, because sine theta is opposite over hypotenuse, SOHCAHTOA, right? So sine theta equals x over 3. That means x is my opposite and 3 is my hypotenuse. So I draw the opposite side here as x and the hypotenuse here as 3. And then I use a squared plus b squared equals c squared to find this guy is the square root of 9 minus x squared. So that's where that diagram came from. I have 2 more examples that I want to work here. So let's go ahead and move forwards. This next one is also going to be an indefinite integral. And it's going to have a free variable in it, or a free parameter in it. It's going to have an extra floating constant. So I'm going to find the integral of 1 over the square root of x squared plus a squared. I want to find this where a is allowed to be any number at all. So my answer is going to have a's in it. According to my trig sub Bible, I want to substitute x equals a tan theta, which means dx will be a secant squared theta d theta. And again, I need to draw my triangle. So if x is a tan theta, then tan theta is x over a, which is the opposite over the adjacent. So my triangle, I label this side as theta, should have the opposite side x and the adjacent side a. And then this side, the missing side here, satisfies this squared plus this squared equals this squared. So this guy is the square root of this squared plus this squared, which is, yeah, the square root piece from my integral. And that will usually be the case. So here's kind of my substitution box. It's got all the good stuff. And now I just start plugging in. Everywhere there's an x, I write a tan theta. In place of dx, I make sure to write a secant squared theta d theta. Fernando asks, would there ever be a time where the missing piece of the triangle is not the square root from your integral? Yeah, if your integral doesn't have a square root. If you're making that substitution for a different reason, then this might not be the case. If there's time, I have a couple of examples I could show you that are like that. And there's 1 or 2 in your homework. Like if this, imagine this was a 3/2 power or a 2/3, something else, right? Something besides a square root, just a weird power of x squared plus a squared. Then this thing would still be the same square root, but over here you wouldn't have that. You would have whatever it is. If there's time, I will show you 1 or 2. But for now, let's go ahead and work this problem. I've got 1 over the square root of x squared plus a squared. X squared is a tan theta. And this is all under a square root, like so. And then my differential term is a secant squared theta d theta. Very important we don't forget that. Now, that's the same as the integral of a secant squared theta divided by the square root of a squared tan squared theta plus a squared. And all of this is being done d theta. And again, the magic happens under the square root. I'm going to factor this a squared leave my numerator alone. Then downstairs here I'll have a squared times tan squared theta plus 1 under my square root. And the beauty is that tan squared plus 1 is secant squared, so the addition will go away. So this becomes integral a secant squared theta divided by the square root of a squared secant squared theta. Because this piece is secant squared theta by Pythagoras. Take a second, make sure you've got each step down in your notes nice and clear. Okay, the magic has already happened. So before we continue, I want to take any questions up to here. We're all clear with why we made the substitution we did? How I knew to substitute x equals a tan theta? Comes straight from that table. Your book, by the way, does have that table in it. They have the expression, the substitution, and the identity. It's on page 486. If you have that PDF that I've made available, it'll be the same page number there. Yeah, it's tempting, right? So here, because you don't need to find your differential floating around in your integrand already, because you're plugging in for your differential, on the one hand, it's easier to do. On the other hand, it's easier to forget. So make sure you know, smash yourself in the head with your textbook or something until it sticks. The a squared down here, I had a squared tan squared theta plus a squared. I factor the a squared out. If I factor a squared out from this piece just becomes tan squared, this piece just becomes 1. So I get the square root of a squared times tan squared theta plus 1. So that's where the a squared here is coming from. There's some truth to that, you know? Yeah. I don't actually recommend smashing yourself in the head, but remember the mistake and learn from it. So usually the way that people remember their mistakes is by getting burned by them, right? Like something unpleasant or painful happens because of a mistake. There will be that experience for you in the homework. You know, if you forget the differential, you'll get the wrong answer. But because the online setting is so unpleasant, it's not the it's not the ideal way to do it. So I would recommend working a few extra problems, like along with some examples on Paul's online notes, for example. If you go to that website that I've posted links to in the modules, you'll have some problems where you can work along with him. Write down the problem, start solving it, and then after you've gotten to this place or something like it, go back and check and see if you have what he has. Do that to yourself a few times. Beat yourself up a little bit if there's something you keep missing before going to the homework. It will help. Please, no concussions, all right? Don't sue me. The secant squareds will not cancel perfectly because downstairs, that secant squared is under a square root. So my next step is to get rid of the square root. The square root of a squared is a, and sorry, upstairs here we have secant squared. The square root of secant squared is secant. So now that I just have multiplication under the square root, no more addition, just multiplication, I can give the square root to those pieces on their own. And what we see is that while the a's cancel perfectly, there will still be one secant left upstairs. So it comes down to this old chestnut. Yeah, okay, good, perfect, yep. Now the integral of secant, who remembers that? This is one of those, no, not arctan. So the integral of secant, remember the trick was multiply by secant plus tangent over secant plus tangent and then make a little u sub. This is one of these which I recommend you just remember. It's the natural log of the absolute value of secant theta plus tangent theta. Remember, odd powers of secant are weird. They often involve natural logs of secants and tangents. Secant cubed is a looping integral. The first power of secant, though, is a u sub problem. We did that on the first day we talked about trig integrals. So if that's a little bit rusty, you might want to go back and look. The trick there is to multiply by secant theta plus tangent theta over secant theta plus tangent theta, and then substitute for the denominator. In any case, my recommendation is that you remember integral of secant theta is log secant plus tangent. But now I need to go back to my original variables. I'm still not done because this is, again, an indefinite integral. We have that triangle up there to help us go back to x's. Secant theta is the reciprocal of cosine theta. Okay, so let me run off to the side here for a second. It seems that our memory of this integral isn't as sharp as I thought. That's all right. So the way you do this it's a silly trick. You only ever use this trick for this integral, which is why I say just memorize the thing. We multiply by 1 in this ridiculous form of secant theta plus tangent theta over secant theta plus tangent theta, and then distribute. So I distribute my secant theta over the top here, and I get secant squared plus secant tangent. The top is now the derivative of the bottom. So you make the substitution z equals secant theta plus tangent theta. And then dz will be, well, the derivative of secant is secant theta tangent theta. The derivative of tangent is secant squared theta. So under that substitution, right, this numerator is dz. So you get 1 over z dz, which is the ln of the absolute value of z plus c, which is the ln of secant theta plus tangent theta plus c. It's a weird integral. It's a weird integral that we talked about a little bit, yeah, when we did trig integrals at first. It's one that you should just memorize. So I'm going to come back to the problem at hand. I need to return from thetas to x's. In order to do that, I need to look at my triangle and interpret this function geometrically. Secant is the reciprocal of cosine. Cosine is the adjacent over the hypotenuse. So secant is the hypotenuse over the adjacent. So remember secant, this is hypotenuse over adjacent, and tangent is the opposite over the adjacent. So I go back up to my triangle and I read those things off. The hypotenuse over the adjacent is the square root of x squared plus a squared. And the adjacent is just a. So that's my secant theta minus tangent theta is just x over a. And you still have your plus c. So that is the value of this integral. It is the natural log of the absolute value of the square root of x squared plus a squared over a minus x over a plus a constant. Oh, sorry, this is a plus, not a minus, a plus. It turns out, and I don't want to go on too far of a segue. Yeah, thank you, Naz. Definitely a plus. Lol. Yeah, a little bit simple. A little bit. It's not too bad. It turns out, if you learned anything about hyperbolic trig functions, that this is also the inverse hyperbolic sine of x over a. That might surprise you. But if you look at this guy, he kind of looks like the derivative of an inverse trig function, doesn't he? If that was a minus instead of a plus, then this would be an inverse sine. It turns out that if you swap that minus for a plus, you get an inverse hyperbolic sine. But I don't think the hyperbolic trig functions are usually discussed too much, so I won't beat you to death with that. Other questions on this one? Yeah, the hyperbolic trig functions are very cool. They do a great job of relating complex numbers to real numbers in terms of trig functions. It is a lot. There's no denying that. This is even this problem, which is a tame problem. As trig subproblems go, this is nice. It's still a lot. They can get much worse. They can get much, much worse. I won't make them too much worse for you, but you can imagine how this process could kind of run away. Maybe you end up with an integral at the end here that requires some biparts, and then you've got trig sub followed by biparts, or something like that. Could get pretty out of hand, and plenty of them do. I'll remind you, if you look on Reddit's r casual math, there was an integral posted there last week that required every method of integration you learn in Calc 2. Trig sub, integration by parts, partial fractions, everything. Integration is hard. There's no getting around it. A big part of the mathematics research that I did in grad school involved evaluating difficult integrals. It's a whole field. There are people out there who are just integrators. It's all they do. But the stuff I'll give you in this class, I promise, will always be accessible. It will always be reasonable. Other questions or comments on this guy? It's fun. Yeah, I like it. It's good stuff. All right. So the next one I want to look at is a definite integral. And I don't think we've done any. Well, we did a tangent sub there. Let's do a definite integral with a tangent sub, and then let's do a secant sub. Zero to one, maybe? Yeah, 0 to 1. So this is a little bit more like the problem we did in class the end of day on Monday. According to my trig sub Bible, the maneuver here is going to let x equal a, which is 1 tan theta. Dx is then just secant squared theta d theta. But I need to change my bounds. When x is equal to 0, I need to figure out what theta is. If I plug 0 in for x here, I get 0 equals tan theta. So theta will be the inverse tangent of 0. Theta equals inverse tan of 0, which is 0. And when x is equal to 1, theta will be the inverse tangent of 1, which is pi over 4. So you got to know your inverse trig stuff. Once we have that, things are easy breezy. My new integral runs from 0 to pi over 4. The square root of x squared plus 1 becomes the square root of tan squared theta plus 1, because x is tan theta. And then dx, remember, is secant squared theta d theta. You might be able to see where this is going, and that might give you a bit of a headache. Tan squared plus 1 is secant squared. So this is the square root of secant squared theta times secant squared theta d theta. So I get the square root of secant squared is secant. So my integral becomes integral 0 to pi over 4 secant cubed theta d theta. Everybody's favorite. This, remember, is a biparts problem. It loops. Rather than running through the looping IBP for secant cubed again, because we've done it twice, why does that feel illegal? I'm not sure. Yeah, what about that feels illegal? Just curious. That's an interesting comment. So there, I get a feeling like that too a little bit from trig sub in general, because we don't have to do anything special to make the differential work. We can just plug it in. Is that what you mean, or are you talking about something else? Oh yeah, it is. It's nice. I mean, that's definitely the point of trig sub, is that it makes square roots go away. Yeah, pretty much. It is, yeah. So the kind of the ethic or the feel behind trig sub is, how do I get rid of shitty square roots? And the magic is that with these Pythagorean identities, if you substitute the right trig function, the square root will always go away. It's very nice. As magical and beautiful as that seems, the integral of secant cubed on its own is awful. I mean, it's fun to do on its own, but I don't want to go through all of that IBP here. So I'll just remind you that the integral of secant cubed is secant theta, 1/2 secant theta tangent theta plus the natural log of the absolute value of secant theta plus tangent theta. And since this is a definite integral, we do it like this. So this requires looping IBP. And we've done it a few times, so I don't want to go through it again. But if you would like to work the secant cubed integral with me, I'd be happy to do that with you in office hours. It's something you should do until you're comfy with it. You run integration by parts once with u equal to secant theta and dv equal to secant squared theta. The output from that will involve tangent squared, which you rewrite as secant squared theta minus 1. Then you distribute a negative and your integral loops. Then you add your integral back over, divide by 2, and you get this. So then from here, we evaluate between our bounds. Since it's a definite integral, we don't have to go back to the x's. We don't have to draw our triangle. We just plug these things in. If I plug in pi over 4, the secant of pi over 4 is square root of 2. The tangent of pi over 4 is 1. And then I have the natural log of the secant of pi over 4 is the square root of 2 plus the tangent of pi over 4 is 1. And then from that, I subtract what I get when I plug in 0. Secant of 0 is 1, but the tangent of 0 is 0, plus the natural log of 1 plus 0. Now 1 times 0, of course, that's 0. This is the ln of 1, which is also 0. So this whole piece over here contributes nothing. So everything we get out from this. It's 1/2 times root 2 plus the ln of root 2 plus 1. And we can use parens there because that is positive. If you want to distribute the 1/2, you can. Yeah, there is no a here, right? So the last problem had an extra constant in there, had a constant a. This guy was just x squared plus 1 under the square root, so there was no a there. So Rakib, this is a separate problem, right? The problem we did before had a constant a in it. It was a different problem. This was the integral of 1 over the square root of x squared plus a squared. And that came out to, so we had our previous example was this guy. It was an indefinite integral. The square root was down squares and there was an a in it. He came out to this. And then the problem we just worked is a totally different problem. It's the square root of x squared plus 1. And it's upstairs, and it's a definite integral from 0 to 1. So I don't expect there to be an a in this guy, just because it's a separate problem. So you might want to go back and rewatch the video, see if maybe the one example kind of blurred into the other. So the value of a, it's true, yes. The table we use to choose our substitution has the symbol a in it. And that a is just the symbol we use for whatever constant is here. The previous example had a free constant in it, but here a is just 1. Yep. Yeah, a is a constant. Here the value of a is 1. In the previous problem, the value of a was just a. It was done in general. Does that make sense? You had an extra constant in the previous problem. Okay. Yeah, go back and rewatch this video. You may want to consider watching it at like half speed. You know, YouTube allows you to speed up and slow down. You might want to change the speeds around so you can follow with your notes and make sure everything gets in where you want it. Other questions or comments on this fellow? Okay. There's one last thing I wanted to do with trig sub, and I promise this last one will be simple. You can rediscover things that you already knew. So there are some problems that, yeah, in a definite integral, if you make any substitution, we have to change bounds. So in that previous guy, our bounds went from 0 to 1 to 0 to pi over 4. Anytime you make a substitution in a definite integral, you got to change bounds. Here is an integral that you guys learned how to do in Calc 1. We know that this is arctan, right? This is the inverse tangent of x plus c. That the derivative d dx of inverse tangent of x is 1 over 1 plus x squared. Therefore, the integral of 1 over 1 plus x squared dx is arctan x plus c. But we can get this with trig sub too. So there's lots of problems that can be done multiple ways. That's one of the neat things about Calc 2 is that there's often many different correct solutions. I wanted to show you how this goes via trig sub. So if I let x be tan theta, dx is secant squared theta d theta, I could draw my triangle here. Since it's an indefinite integral and I'm doing trig sub, I should. But for this particular guy, we won't end up using the triangle. Just for practice, though, let's do it. Tan theta is the opposite over the adjacent, and x I can think of as x over 1. So I think of this as my opposite, and this is my adjacent. And this guy is going to be the square root of 1 plus x squared. So I wanted to do this problem because it answers Fernando's question. Will the missing side of the triangle ever be not the same as the piece from your integral? Well, here it's the square root of 1 plus x squared. Here I didn't even have a square root. Right, so this is an example of a problem that we can solve with trig sub, where the missing piece of my triangle is not showing up in my integral anywhere. So Caesar asks a good question. I thought trig sub was just for things with square roots. Not necessarily. Because I have this 1 plus x squared down here, it still looks trig subby, even though it's not under a square root. If it was under a square root, I would need trig sub. But I can still use trig sub, because this is something that will simplify nicely due to the Pythagorean identity. Other cases where you might use trig sub, even though there isn't a square root, is if this was raised to like a 3/2 power or some weird power. Any power where the denominator was even. Yeah, it's sneaky, it's cool. So while we definitely need trig sub for a lot of the square root integrals, we can use it in other places too. If we do this, then my integral becomes 1 over 1 plus tan squared theta times secant squared theta d theta. And the 1 plus tan squared downstairs, that is secant squared. So this is 1 over secant squared theta times secant squared theta d theta. And the secant squareds cancel perfectly. So you just end up with the integral of d theta, right? 1 d theta if you like, which is theta plus c. And then since x is tan theta, we take inverse tangent of both sides to see that theta is the inverse tangent of x. So this is what we thought it would be. It's arctan. It's the inverse tangent of x plus c. And this is just one example of an integral that can be done with trig sub, where your triangle, his missing piece doesn't show up in the original problem. All the other inverse trig stuff can be done like this too. So if I had 1 over the square root of 1 minus x squared, I could get that that is the inverse sine function via trig sub, if you don't remember the derivative of arcsine. There are sort of 2 other little things I want to do. We haven't had practice with a secant substitution yet, and then there's something involving completing the square. The completing the square stuff I'm going to post to a module in Canvas. It's a little bit hairy, but there are some problems that require it. So take a look at the Canvas modules later today. Around 3 p.m. I should have that stuff up for a supplemental on completing the square. If I wanted to, for example, integrate the square root of x squared plus 2x, this doesn't look trig subby right away because it's not x squared plus a constant, it's x squared plus 2x. The way you do this, and I'm not going to go through the whole problem now because this particular one is horrible. The way you do this is by completing the square. So if you don't remember how to complete the square, I think I gave you one thing like this in your homework. You will need to remember it. X squared plus 2x is the same as x squared plus 2x plus 1 minus 1. So I add and subtract 1. I've added 0. I've not changed the value of that function at all. It's the same function. But now if I group this piece, this is the same as x plus 1 squared. So this is really the integral of the square root of x plus 1 squared minus 1. Ah, fuck it. Maybe we'll do it. Let's do it. All right, yeah. Go ahead, and if you haven't written this down because I said we weren't going to finish it, go ahead and write it down. We're going to do it. Okay, so this step here is called completing the square. We complete the square underneath the square root in order to make the thing look trig subby. Now this will be, if you look back at your trig sub Bible, if I think of this as u squared minus 1, that's a secant substitution. So let me move this up. To do that integral, I'm going to let x plus 1 be secant theta. Taking derivatives on both sides, I see that dx, right, derivative of 1 is 0, so I just get dx on the left, is secant theta tangent theta d theta. And then I also need to make my triangle. Secant is the reciprocal of cosine. So that's the hypotenuse over the adjacent. I think of x plus 1 as x plus 1 over 1. So that's my hypotenuse over the adjacent. And then this side will be the square root. You can write it like this. I think that's the way that makes most sense given what we've done. And that's your little trig sub box. If I had, so here's the thing. If you're having trouble seeing this right away, go back here and make, you can do the little u sub, u equals x plus 1, du equals dx, and then your integral will look like the square root of u squared minus 1 du. So it's not a tangent substitution, it is a secant substitution. This piece right here, this piece is u squared. So it's u squared minus 1, so that is a secant sub. I prefer to do it like this. I prefer to do it in one step, but you could do this and then do the secant substitution. U equals secant theta du equals secant theta tangent theta d theta with your triangle like this. They're the same. So the big box at the top gets it all done at once, or you can break it down into these two steps here, where you do a little u sub and then your secant sub. So in your trig sub Bible, I used the symbol u instead of the symbol x because you can make the substitution with any linear function of x. So here I had x plus 1 equals secant theta. And I can go straight to my trig integral. Or I could do the little u sub u equals x plus 1 to get my integral to this form, and then do this little secant substitution. Faster to do it all at once. Cleaner. That's what I'm going to do. But you could have done this little thing instead. Either way, where we're going to end up is with the following trig integral. So I'm going to go from this guy. So straight from here to here. X plus 1 is secant theta. So x plus 1 squared is secant squared theta. Then I've got my minus 1, and that's all under the square root. And that's what you would get here also, right, if you did this substitution there. And then my differential term, dx, is secant theta tangent theta. So whether you do these two things or this one thing from here, you'll land here. For the purposes of your notes, I recommend just writing one of them down. All right, I would omit this. However, if this big table up here scares you, or if you just don't like it, if it seems like too much in one step, that's perfectly understandable. You can do this. But either way, you're going to land here. All right, so my integral from the very top up there is equal to this integral. And I've just done this substitution. Secant squared minus 1 is tangent squared. My differential stuff still coming along for the ride. The square root of tangent squared is tangent. So because the square root of tangent squared is tangent, I have secant tangent times tangent is secant theta times tangent squared theta d theta. This is also an unpleasant integral. This is another looping IBP problem. You might remember this from your last homework. I gave this to you on homework 3 or 4, the trig integral homework. One way to do it is to rewrite tan theta as secant squared minus 1, and then you'll end up with the integral of secant cubed minus the integral of secant. Since we haven't done it directly, let's go ahead and do that. This is about as bad as trig sub can get. So from here, I'm going to run IBP. For dv, I'm going to pick secant theta tangent theta d theta because I know how to integrate that. And for u, that just leaves me with tangent theta. Lipet doesn't help here. So I'm going to zoom in. This is now my task. du then is secant theta tangent theta d theta. Oh no, sorry, secant squared theta. and V is secant theta. So here's my IBP table. I get out U times V, which is secant theta times tangent theta, minus the integral of V du, which is secant cubed. My goal is to make this integral show back up. So I'm going to split the secant cubed into secant squared times secant. I guess I could have saved a step by just leaving it as that, sorry. And then rewrite secant squared in terms of tangent. Secant squared is tan squared theta plus 1. Then I distribute the secant. And then I distribute this negative and I split up the integral. So I get secant theta tangent theta minus integral secant theta tan squared theta minus integral secant theta d theta. I'll give you a second to catch up. Y minus, because I've got this negative here, which is going to get distributed to this and to this. So that negative, again, this is why I always put my integrand in parentheses, to remind me that things distribute. The differential term distributes, shit, and I suck. And the negatives or any constants out front distribute. The magic from here, I'm going to add this piece back up here. So there's some funky trig sub followed by some funky IBP. Get that centered. Let's zoom out a little bit. All right. So my integral, which became secant tangent squared, is equal to this. So my integral, which is equal to the integral of secant theta times tan squared theta d theta, is equal to secant theta tangent theta minus integral secant theta tan squared theta minus integral secant theta d theta. And again, I left off this d theta, I'm sorry. Bad habit. So I'm going to add this over. 2 times the integral of secant theta tan squared theta d theta is equal to secant theta tangent theta minus the integral of secant theta d theta. And again, my integral is the integral of secant times tangent squared. So my goal is to solve for this. Divide by 2. equals 1/2 times secant theta tangent theta minus, and remember the integral of secant theta, that's the natural log of secant theta plus tangent theta. And now I write my plus c. My integral is equal to this. This is equal to this. Therefore, my integral is equal to 1/2 secant theta tangent theta minus the natural log of secant theta plus tangent theta plus c. And then finally, we go back to our original variable. So I bring this guy back in. That was my substitution table. Because I chose to do everything at once, right? I didn't do the little u sub. I just let x plus 1 be secant theta. I can go back in a single step. So I get my integral, which was the integral of x squared plus 2x is equal to 1/2. Secant theta is x plus 1. Tangent theta I get from the triangle. It's the opposite over the adjacent. So that's the square root of x plus 1 squared minus 1 minus the natural log of secant theta, which is x plus 1, plus tangent theta, which is the square root of x plus 1 squared minus 1. Close log, close bracket, plus c. All right. This is as bad as these get for you guys, but it's not as bad as they can get. Be clear about that. I will never give you anything worse than this. I promise you that much. And this is a good example because it involves completing the square and then trig sub and then IBP. It's a hard fucking problem. But it's a good problem to make sure you can follow it. Just remember the number at the end. So the 1/2, there was a question there, where does the 1/2 come from? It's coming from this 2. Do you understand where that 2 came from? If you look back at this line, you have integral secant tangent squared equals secant tangent minus integral secant tangent squared minus integral secant. So I'm going to add this piece to both sides. I add that piece here. So I get this integral plus itself equals secant tangent minus integral secant. That integral plus itself is 2 times that integral. So I have 2 times that integral equals secant tangent minus integral secant. That's where the 1/2 is coming from. I divide both sides by this 2 to get this integral alone. That's what I want. That's the 1/2 over here. I divided by 2, secant tangent, and then the integral of secant is this. It's messy. So the 2 is what what is the 2.5% all of the original integral? It's like 7. I throw it out. Yeah. So if your original integral had some other constant, then you're not going to get a 2 here. You might end up with a 5 here. Or you might end up with, if you had like 7 of these equals this, then when you add this back over, you'd have an 8 here. And so you'd have a 1/8 here. So there's 2 ways to handle that stuff. You can either pop the constant out at the very, very start and then run through it without any constants, and you'll have a 2. And then you multiply your constant back in at the end. Or you keep the constant in there the whole time. And you'll have to juggle it around, all this stuff. But when you go to add back over here, you'll end up with something other than this 2, like a 5/8 or something, and then you divide that over. So practicing with the constants in the looping IBP stuff is complicated. The easiest problems to practice that stuff on, easy way to, it's not easy, but the easiest way to practice that stuff and get good at it, do this integral. E to the ax times the cos of bx. Keep a and b in there as constants. And then force yourself to be careful with the constants. The stuff that comes out of this is a little bit complicated looking. It should end up involving like 1 over a squared plus b squared. But if you practice this integral, right, do this once, but do it carefully, like on a board, then you'll get good at juggling the constants in these looping problems. The IVP here is tough. I'm not going to pretend like it isn't. You might benefit from going back and just working like from here. You know, forget about the fact that this came from trig sub. Just come back and work the secant tangent squared integral on its own. That on its own is a challenging looping IVP problem, and it's in your homework. It was in homework 3 or 4, homework 4, I think. Homework 4. Okay, yeah, thank you. Yeah, no, that's okay. You'll always end up with a 1/2 if the problem, you'll always end up with a 1/2 in the secant cubed or secant tan squared or e to the x cos x or e to the x sin x integrals if there are no other constants involved. But if there are constants multiplying your integral at the start, or if there are other constants inside the e to the x or cos x function, then you'll end up with different looking constants at the end, and that's okay. Towards the end of the class, this semester, this summer, I'll be able to show you a really slick, fast way to do this integral. The e to the ax cos bx integral can be done very quickly if you're willing to work with complex numbers instead of sticking to real numbers. If you want to see that, search for Arthur Matic. Make sure I send this to everybody. Google search Arthur Matic, MIT, complexifying the integral. More tricks on looping IVP. Yeah, unfortunately, I also have to get out of here. So this is where I'm going to end our meeting for today. Sorry. Hello? God, I'm sick of that shit. So yeah, I do have to switch over to my office hour now. So definitely take a look at that Arthur Matic video, complexifying the integral. I pasted a search keyword into chat there. The spelling of his name, Arthur Matic, MIT, complexifying the integral. It's from a differential equations class, but he's going to be looking at integrals like this guy down here. And he'll show you a slick way to do it. And I'll be able to show you that at the end of the semester after we have Euler's identity. But for us right now, the best thing you can be doing to practice is to work the homework problems and work them honestly. The secant tangent squared integral is in there. There is one completing the square followed by trig sub problem in this week's homework. And if you're able to work through those patiently, carefully, correctly, then you will be okay. So continue grinding on that homework. Remember my advice, homework 4 should be done. If it's not done, get that shit done now. And then get into homework 5. Make sure you get a good chunk of homework 5 done before our next meeting on Friday, when I will be giving out the study guide. And that way you can focus primarily on the study guide over the week leading up to the exam. If you want to chat more problems or anything like that, I will be switching over to my office hour now. And I hope to see you guys there. Also remember to look in the modules on Canvas for some more resources on trig sub, specifically completing the square. Of course, yeah, I hope you guys have a lovely afternoon. If I don't see you, I'll see you on Friday.